example, problem 9, page 584, solve this differential equation. So we can separate the variables, okay? And then we'll see whether or not we can, well, we see if we can separate the variables so we can use this technique. Are they multiplied together, in other words? Well, even though we've actually got a negative sign here, we can think of this as one whole term that's then multiplied by something else, as we'll see when we try and separate the variables. So sometimes it's not easy to see that separation of variables methods works, but if we try separating the variables on this one, we can see if we take the dx over to the right hand side, so if I multiply both sides by dx, I get 4x y dy equals y squared minus 1, if you put that in a bracket now, times dx. So I can do that. Yeah, so we can bring the y squared minus 1 underneath. So that's a y there. So we can bring the y squared minus 1 underneath. We get 4xy over y squared minus 1 dy equals dx. Yeah, they are sort of swapping places, aren't they? I think. You mean, think of going like that goes up there and this comes down here. Yeah, you can do. Yeah, yeah, yeah. But now, of course, we've got the 4x that could go underneath over here. So dividing both sides by 4x, we've separated variables. Y over y squared minus 1 dy equals 1 over 4x dx. It might make it easier for us actually if we leave the, we can do it either way, but if you left the 4 on the top, that might in hindsight have actually made it a little bit easier because we just left with 1 over x. But it doesn't matter, it'll work out the same either way. Yes, that's right, 4y over y squared minus 1. So you could have left the 4 on the left hand side. In fact, you could try maybe doing this again with the 4 left over there and see what effect that has. Okay, so now we've separated the variables, we just integrate both sides. Integrate the left hand side with respect to y, integrate the right hand side with respect to x. If we just rethink of this for a second, so this is like the integral of y over y squared minus 1 equals 1 over 4 integral 1 over x dx. Think of this like that. We've got to do integration using algebraic substitution. We use algebraic substitution here. We let y squared minus 1 equal u. Now, can you remember what we do next with this now? So now we differentiate and we get du by dy equals 2y, because the 1 disappears and the 2 comes down. Yeah. No, we're just differentiating u with respect to y. So now, do you remember with this method, we bring the dy up and bring the 2y down, so dy equals du over 2y. That's this method of algebraic substitution. dy equals du over 2y. Rewriting it so it looks better. remember what's going on in this, what we're doing in this algebraic substitution, we're going to let this whole term underneath here equal u. But that means we need to now differentiate in terms of u, and the y, this other y here, must disappear for it to work, if you remember. So what we do is we let u equal y squared minus 1, we differentiate that, and then rearrange it so dy equals du over 2y. Then, instead of dy here, we write du over 2y, and we hope that when we do that, the y's cancel, which they're going to do. So, carrying on this left-hand side, the integral of y over y squared minus 1 dy becomes the integral of y over u multiplied by du over 2y, but with respect to du over 2y, substituting in u equals y squared minus 1 and dy equals du over 2y. Now we see that the y's cancel. So this equals, bringing the 2 outside the integral, a half the integral of 1 over u du. So this equals a half the natural log of u, which is a half the natural log of y squared minus 1, substituting back in what we let u be. So we've done the left-hand side. We've integrated the left-hand side. It's the same process that we were doing before. We've still got to separate the variables, going back to the basic idea, separate the variables and then do the integrals. Here they are. Unfortunately, this time, this integral involves an algebraic substitution. So what we've just done on the left-hand side now equals this. Well, the integral of 1 over x is log x, isn't it? So we've got that, a half log, therefore, a half log y squared minus 1 equals, bringing this right-hand side down, okay, doing this integral, a quarter log x. Plus c. Yeah. So, yeah, so we've just multiplied both sides by 4 to get it into this form here. Yeah, and as you say, that's the implicit form. Yeah. And so we now need to do something to do that, to get y on its own. It's not a straightforward solution, this one. I wish I hadn't done it. But let's have a look at it. So what did you do first of all? We'll go from there. Right, so therefore log equals a half log x. Let's see. Now what's going on here, and this is the awkward bit, is that if you think about logarithms and what they mean, if I have the log or natural log of a to the b, if you remember why we did that, when we use logarithms to solve indicial equations, that meant that the b can come down and become a multiply, remember? So the other way to think of this is that a half, which is here, could actually be a power of x. So I could think of this as log y squared minus 1 equals the log of x to the half plus c. And that's an awkward step because it's asking you to recognize that this is using laws of logarithms. We can rewrite that like that. And then we take e to the of both sides. We put the exponential function to both sides. So therefore, y squared minus 1 equals x to the half plus e to the c, effectively. You could do, but you wouldn't, because we only put it as u as a means of being able to integrate it up here. And once we've done the integration, we let u be what it was originally, which is y squared minus 1. X to the half is the square root of x, isn't it? So we've got y squared minus 1 equals the square root of x plus some constant. Well, now I could take the 1 over here and then square root both sides, and I could get y. So I've done the hard work now, haven't I, to get y on its own. So I can now rewrite it as y equals something. And we need to think about how we get this value for k.